Chapter 5 is all about chemical bonds, specifically covalent bonds. And so these are theories that help us to explain how and why atoms attach to form molecules, and why some combinations are stable while others are not. So why can we have H2O but not HO or H3O as stable molecules? It helps us predict the shapes of the molecules and the chemical and physical properties. Because the shapes are what governs how molecules interact with other things. So the most basic bonding theories is the Lewis theories. It really emphasizes that the valence electrons are the active components in the bonds. And it helps us to predict molecules being stable, their shape, their size, and their polarity. And I'll say it doesn't really help us predict the shape, but it will be a fundamental thing that we build off of later in order to think about the shape. So just because we're learning it, it's the simplest one, doesn't mean we're going to get rid of it. We're just going to build upon it later. So chemical bonds form because they lower the potential energy between the charged particles that are in the atom. So the nuclei, the electrons, and the nucleus to the electrons. Remember that the nuclei, they're both positive, so there's going to be a repulsion there. The electrons between atoms are also going to have a repulsion, but the nuclei of one element and one atom and the electrons of another will have an attraction. So this will be that we'll have a chemical bond in a form where there is a minimum or the lowest potential energy of the attractions between these particles. So when we have the bonded atoms have a potential energy that is less than the potential energy of the individual atoms, that's more favorable, so we're going to form a bond. We have different types of bonds depending on the types of atoms. So metal, nonmetal, that's going to be an ionic bond where the electrons are transferred between the atoms. We're going to have nonmetal, that's that covalent bond when we have molecular compounds where electrons are shared. That's going to be the focus of this chapter. And metal will be a metallic bond where electrons are pulled. We'll talk about that next semester. So even though molecules have bonds where that we have electrons being shared, there won't always be an equal sharing. So when we have an unequal sharing, then to some extent there's a slight degree of ion formation. We call that a dipole. So we classify molecules as pure covalent if the electron transfer is pretty small to where they don't actually act like ionic compounds. If the sharing is unequal enough to produce a charge, a slight charge, we call that a dipole in the bond. That is called a polar covalent bond. So when we have atoms that are not the same, then generally we have that unequal sharing. So for example, in this picture we have chlorine and hydrogen. Now chlorine is a halogen, so it really likes electrons because then it gets close to being like a chloride. So even though chlorine and hydrogen are sharing the electron, chlorine likes electrons a little bit more than hydrogen, so it's pulling on it. So we'd call that being electron, it would be electron rich, and then hydrogen would be electron deficient. So so that's what a polar covalent bond is, where the charge with the more negative side, so that'd be chlorine in this case, gets a partial negative charge, And the part that isn't seeking the electron as much is electron deficient, that gets a partial positive charge. So we call that wanting to take the electron as electronegativity. So it's the ability of an atom to attract a bonding electrons to themselves. We call that electronegativity. So something that has a high electronegativity, so that's these elements over here, those are going to be pulling on the electrons really hard. So fluorine is the most electronegative, and francium is least electronegative. So it's kind of following the trend of like effective nuclear charge. And the noble gases are not assigned them because they already have, or they're full octet, so they're not really seeking electrons. But keep in mind that noble gases can bond. They're just, they don't really have an effective nuclear or a electronegativity. So what we'll do to determine if something is polar or nonpolar in its bond is we will look at the difference in electronegativity between the atoms in the bond. So we're going to look up the electronegativity. So hydrogen has a 2.1. Fluorine is 4.0. So that electronegativity difference is 1.9, so pretty big. And so how we draw that dipole is fluorine's pulling on the electron, so I draw an arrow towards fluorine since it's pulling on it. And then hydrogen is left with a slight positive, so I make that little, like a plus sign there. So you can see here we have our electron, so this is hydrogen, it's electron poor or deficient. And then chlorine is taking all those electrons, so it's electron rich. So in order to determine, we basically have to have some kind of cutoff. Keep in mind this is a spectrum of whether something is polar or nonpolar or even ionic. And so we have to have a cutoff, but the cutoffs can vary from reference to reference. So as far as our book goes, this is where it'll be. So if the difference in electronegativity to the bonded atoms is 0, we call that a pure covalent. That means that there is exactly equal sharing of the electrons in the bond. If it's between 0.1 and 0.4, we call it a nonpolar covalent. It's still not pulling hard, but it's not exactly 0. If it's between 0.5 and 1.9, this is called polar covalent. So this is enough to produce a stronger dipole to where we have that partial positive, partial negative. And if it's greater than or equal to 2, we call that an ionic bond. So again, we have the small, we call that covalent. 0.4 to 2 is polar covalent. And then large is ionic. So here is that pure covalent, what's called covalent, polar covalent, and then enough pull that they actually are completely, the electrons are completely taken, is ionic. So a dipole moment, mu, is the measure of the bond polarity. We're not going to actually calculate that in the class, but it is a way that scientists can measure it. It's been measured with the Debye. It's when we have that positive and negative end. There's another way, it's called the ionic, percent ionic character. And it's basically a percent of how much the bond is like an ion, or if it's, so pure ionic would be If it was completely ionic, it'd have 100% ionic character. Notice even things that we consider ionic compounds like lithium fluoride, potassium fluoride, and such, they're not quite 100% ionic. So it's that spectrum I was telling you about. So this is kind of a nice way to visualize how much percent is the electron actually transferred to the other atom. So we're going to determine if these are polar or non-polar. I'm going to let you do it. I encourage you to pause, and then I'm going to put up the answers as we go. Okay, so we just take the difference. We look up on the table the ionic or the electronegativities. We take the differences to find out. So we have ionic for strontium and fluorine with the electronegativity difference of 3. Nitrogen and chlorine have a delta electronegativity of 0, so it's covalent. Nitrogen and oxygen are polar covalent with delta En of 0.5. Iodine with iodine is 0, so that's pure covalent. We have cesium and bromine that are ionic with 2.1, and polar covalent for phosphorus and oxygen with an electronegativity of 1.4. So now we're going to actually start to build molecules. So basically with this Lewis model, we are going to have atoms bond, so either gain, lose, or share, in this case share, so that way they have that noble gas like configuration. So 2 s electrons, so basically 8 electrons. Remember, nonmetals in the second row only can have, they must obey the octet rule. If you get into the third row or below, now we have D, because remember we have the first d orbital is 3d. So if n equals 3, so that third level, so if I'm looking at the periodic table, row 1, row 2, row 3. So if you're on that one, you can accommodate more than 8 electrons if you're in the center, if you're a central atom. So the first step is to write the correct skeletal structure. That sometimes is the trickiest part. But usually the less electronegative atom is in the center. So, which is funny because oxygen is not less electronegative than hydrogen, but hydrogen will always be a terminal atom, so it will only be connected once. So usually more electronegative are terminal, usually. Then you're going to determine the number of valence electrons. You're going to literally add it up. So for hydrogen and bromine, we have 1 plus 7 is 8 valence. I want you to write that on your paper as you're solving the problems, because you're going to check back with that. That's important. If we have a polyatomic ion, the charge is going to be considered. So if I have nitrogen, has 5 valence. We have 2 oxygens, they each have 6. And then I have a negative charge. This means I have an extra electron. So I have a total of 18 valence electrons for nitrite. Then you're going to distribute the electrons. I like to put them on the terminal atoms first and then fill in to the central atom as needed. Basically, you're going to connect with bonds with that skeletal structure, fill in the terminal atoms until you run out of electrons from step 2. So in this case, you want to give everybody an octet until you run out of electrons. If you run out of electrons before everybody gets an octet, you're going to form double and triple bonds to give everybody an octet. Remember, these are the ones that can double bond. You'll figure it out. Okay, so if I have carbon dioxide, so first thing, less electronegative is carbon with these oxygens on it. I'm going to have 4 valence electrons from carbon, 6 from each of those oxygens. I have a total of 16. So I have 4 electrons in the bonds. So I'll go 4, 6, 8, 10, 12, 14, 16. So there's all of the electrons that those elements provide. But notice there's not enough electrons. Carbon doesn't have an octet. So what I'm going to do is I'm going to get rid of those set of electrons and move them into bonds. So instead of being purely on oxygen, it's going to, a bond will have been formed. Oops. So there we go. Now carbon has 6. So if we look at carbon, what's going on with carbon? It has 6 electrons. 2, 4, 6. So now I'm going to get rid of another set. I'm going to just do it over here, although it technically doesn't matter which one, as long as you move a lone pair. And I'll give that to carbon. There we go. Share it with carbon. So now we have still 16 valence electrons, and now carbon has 2, 4, 6, 8. So CO2 looks like that. Carbon monoxide, we have 4 plus 6, so 10 valence. So I have CO. I'm going to fill in those 10. 2 from the bond, 4, 6, 8, 10. So now I'm going to, I need to make some of those, so carbon doesn't have an octet. So I'm going to move this set here to be a bond. So now carbon has 2 from the lone pair, 4, 6. So getting close. I'm going to erase one more from oxygen, and now carbon, and move it to a bond. So now each of those have 8 electrons, and we have our 10 valence total. For NH3, I have N with each of those hydrogen. Here's my skeletal structure. Notice we could do valence electrons or skeletal structure first. So here's my valence, 5 from nitrogen, and then 3 hydrogens times 1, so 8. So hydrogen, remember, likes a duet, so the only person who I can, or the only atom I can add to is nitrogen. So I have 2, 4, 6, and then 8 from the lone pair. So that's done. For this molecule, let's do valence electrons. I have 2 times 1 for hydrogen, plus 4, plus 6, so a total of 12. So I have carbon, hydrogen, hydrogen, oxygen. I know it happens to look like that, but if you didn't know, I'd have to tell you what the skeletal structure is so you can kind of do it the right way. So I have 2, 4, 6 in bonds. So I'm going to fill out terminal, 8, 10, 12. Okay, so my valence electrons are all on there, but carbon doesn't have an octet, so I'm going to remove one of those sets of valence electrons and make it a bond. Okay, now everybody's happy. With ammonia, I have, this is ammonium, so I have 5 plus now 4 times 1 minus 1, because that nitrogen, this plus means I'm taking away an electron, so 8. So I'll fill in plus 4, 2, 4, 6, 8. Oh, that's done. Cool. Now this ion, ClO2 minus, so I have 7 plus 6 times 2 plus 1. So that's 12 plus 10, or plus 8, so 20 valence electrons. So I'm going to have ClO. So now I'm going to do 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. As far as you're concerned at this point in your life, that is good enough. I'm going to let you pause and I'll write in these, and then you can come through and check your answer in a sec. Okay, feel free to pause here, check your work. Okay, moving on. So the next part we're going to talk about is resonance versus formal charge. So this is going to help us to write the best possible Lewis structures we can. So resonance is when we have 2 or more possible Lewis structures for the same compound. And formal charge is like a bookkeeping way that we can keep track of how electrons are on different resonance structures and figure out which one's going to be the best. So first with resonance, the Lewis theory basically says that electrons, especially those in the double bonds and the lone pairs, those can move around. So we call that delocalized. When there is some delocalization, that helps to stabilize the molecule. Make sure you keep in mind that Lewis, or these resonance structures, differ only in the placement of the bonds, so the position of electrons. Not how they're connected. That's a whole different thing. The actual molecule actually has a combination of resonance form that's called a hybrid. A resonance hybrid. So for example, with ozone, we can have the double bond be between the left oxygen or the right oxygen, but what's really happening is kind of flip-flopping in between them. So again, they have to have the same connectivity and same number of electrons. Follow the same rules as normal. Their formal charge must be the same. We'll talk about that in a sec. And then the best structures have fewer and smaller formal charges. Oops. And if they do have a formal charge, the negative should go on the most electronegative atom. We'll talk about that in a sec. So here we have nitrate ion. Let's draw the Lewis structure and we'll have the different resonance forms. So we have 5 plus 3 times 6 plus 1. So we have 24 valence electrons. So for nitrate we have N O's, and then we're going to fill in valence. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So notice we could either create a double bond on any of those electrons or any of those oxygens. So I'm going to first do it here, that double bond, and remove this valence pair. But I could have equally done it on the others, so that will be what I do down over here. So there's another one, and then the last one will be with that double bond through the center one. Pretend that one's not there. And then the hybrid, resonance hybrid, would look something. We won't draw the lone pairs. It'll look something like that, where that double bond is resonating between all of those structures. Okay, formal charge. This helps us to figure out the best resonance structure. So the general rules are, if we have a formal charge, it needs to be equal to the charge of the molecule. So if it's neutral, it should be 0. They should all add up to be 0. If it is an ion, it should be equal to the charge of the ion. We're looking for small or 0 formal charge. And when you have to have a formal charge on one of your atoms, the negative formal charge should be on the most electronegative element. So let's practice. So basically the gist is, I'm actually going to count. You count the number of valence electrons in the atom, subtract the number of non-bonding electrons minus the number of bonds. So if I have HF, So for hydrogen, hydrogen has one valence electron. It has 0 non-bonding electrons, and it has 1 bond here. So its formal charge, 1 minus 1, is 0. Formal charge for fluorine, we're going to do the number of valence electrons for fluorine, 7. How many lone electrons? 1, 2, 3, 4, 5, 6. So 6 non-bonding. And then also has 1 bond. So 7 minus 6 minus 1 is 0. So the formal charge for fluorine is 0. So that's good. They have a minimum formal charge. So let's practice that some more. Okay, so we're going to practice for SO2. Here's the Lewis structure. Here's one of the resonance forms. So for that left-hand oxygen, so this one right here, I'm going to take my number of valence electrons from oxygen, 6, minus how many non-bonding electrons, so 1, 2, 3, 4, minus how many bonds, 1, 2. So 6 minus 4 minus 2, that equals 0. So that left oxygen has 0. Now sulfur, it has 6 valence electrons on sulfur. We look on the periodic table. It has 2 electrons, 2 non-bonding electrons, and then it has 1, 2, 3 bonds, so minus 3. So sulfur has a formal charge of plus 1. And then our right-hand oxygen, 6 valence electrons minus 1, 2, 3, 4, 5, 6 non-bonding electrons, and 1 bond. Minus 1 equals negative 1. So sum them all up, add all of those formal charges together, we get 0, which is good because it is a neutral molecule. So with regard to formal charge, we're going to, again, draw the Lewis structures, find the different resonance structures, assign formal charges, and then you can... Okay, then what you get to do is you can actually move electron pairs from atoms with a negative formal charge towards atoms with a positive formal charge to help kind of neutralize those. If the positive formal charge are in the second row, you can only move them to where you can get multiple bonds, but you can't extend octets. If that positive formal charge is in the third row or below, you can move it to be electron pairs to reduce the formal charge. And that's okay even if you get expanded octets. So we'll talk about that a little later. So let's just practice with these 2 resonance structures of carbon dioxide. So we're going to deal with each atom separately. So let's do this oxygen first. So 6 valence electrons from oxygen, 1, 2, 3, 4 non-bonding electrons, and 1, 2 bonds. So formal charge of that oxygen, 0. Carbon has a formal charge of 4 valence electrons. It has 0 non-bonding electrons and 1, 2, 3, 4 bonds. So it has a formal charge of 0. And this oxygen on the right is symmetric to the one on the left. So 6 valence electrons, 4 non-bonding pairs, 2 bonds. So formal charge of 0. Structure B. So this oxygen is different. It has 6 valence electrons. It has 2 non-bonding electrons and 1, 2, 3 bonds. So it has a formal charge, subtract those, of positive 1. This carbon, 4, 0 non-bonding, 4 bonds. They're just distributed a little different, so 0. And then this oxygen, 6 valence electrons, 1, 2, 3, 4, 5, 6 non-bonding and 1 bond, so that has a negative 1 formal charge. So we look at those total. They all add up to 0, which is good, but this structure A is going to minimize our formal charge. So we have less than 0 formal charges on a lot more atoms, so that's going to be the more stable, and that's how we actually draw carbon dioxide most often. So I'll practice again, give you some time, make sure you pause right now to practice. I'm going to fill it in, and then you can check your work. Okay, so we filled these in. Structure A gives us formal charge of negative 1 on the oxygen. B gives a negative 1 on the nitrogen, and then C gives positive 1 on oxygen, negative 2 on nitrogen. So we want to minimize. So structure C will not be it. Then look at A and B and see who has the negative on the most electronegative element. So we're looking at nitrogen versus oxygen. We go look at our electronegativity chart. Realize the highest electronegativity is oxygen. So structure A is good because the negative charge is on our most electronegative atom. I'm going to let you pause here and practice this one to figure out the best structure for dinitrogen monoxide. Okay, so for this one, we'll look at the one that has the higher formal charges on more things, so that's structure C, so it will not be structure C. So then we go look here who has the negative formal charge on the most electronegative element, so that will be structure B, because oxygen has that -1 versus the nitrogen here. Okay, now we're going to draw the resonance structure for nitromethane. I'll give you we'll assign formal charges. So we have 4 valence electrons from carbon, 3 from hydrogen, 5 from nitrogen, and 12 from oxygen. So that gives us 7, 12, 24 valence electrons. This skeletal structure looks like this. Valence electrons here, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So our various, so let me draw the other one. So my resonance structures, I'm going to have one there, or double bonds there. So the formal charge assignments will be similar. I'm going to pause, calculate the formal charges of everything, and put them next to the element, and know it'll be similar on the other molecule. So here is diazomethane, which looks like, so we have 4 plus 2 plus 10, so 16 valence electrons. So we have carbon with my hydrogens, nitrogen, nitrogen. So 2, 4, 6, 8 in bonds, 8, 10, 12, 14, 16. So there are a couple different resonance structures for this guy. So I could either, well, carbon definitely needs some valence electrons, so I'm going to share that electron there. Now nitrogen is missing one, so I'm going to share one there. Alternatively, I could have, so this gives me a formal charge, 0 for my hydrogen, 0 here. This nitrogen has 5 minus 0 minus 4, so a positive 1. And then this nitrogen has a -1. So they're the same element, so this would be fine. Alternatively, I could have carbon, nitrogen, and then my hydrogens, and then have a carbon like this. Let me make sure I have enough electrons. 2, 4, 6, 8, 10, 12, 14, 16. That works. Here, well, carbon will have, so hydrogens will still be 0. This nitrogen is still +1. Now this nitrogen is 0. And this carbon is +1. So then you want to, I lied, -1. So now we say, okay, who's more electronegative, carbon or nitrogen? And it's nitrogen, so this is the structure that would be most likely for diazomethane. So some exceptions to the octet rule. First one is when we have an odd number of electrons. So odd electron species. These are called free radicals, so dangerous. Having an odd number of electron means you're going to not be able to have a full octet. And so somebody's going to have fewer than 8 electrons around the central atom. For Lewis, you cannot write legitimate structures because it's too simple with this theory. I will never give you a Lewis structure to draw that would have odd electrons. So if I did, or if you count an odd number, then it's probably the wrong number of valence. So you'll have to go back and check it. For example, nitrogen monoxide has 11 valence electrons, so we can't do that. This molecule does exist as a molecule, but like I said, Lewis is not sophisticated enough. Now the most common ones are going to be exception 2 and 3, and that is, exception 2 is incomplete octets. So these are the ones who do not want 8 electrons. So remember, hydrogen only wants 2, boron prefers 6 total, not 8. And then even beryllium, Be likes 4 if it does covalent bonding, so keep that in mind. So Bf3 would be like that, and that's fine. Well, it'll have its, fluorine will have an octet, but boron is totally fine. This has 24 valence electrons, and this gives it 24. It's happy. BH3 has 6 valence electrons, and this is how it looks. So it's happy. So boron, remember boron, 6 electrons. I'm sure it'll show up again. Last one is expanded octets. I like these ones. These are molecules that are able to have more than 8 valence electrons around the central atom. Remember, it's if they're in the 3rd period or below, so n equals 3 or lower, only if they're the central atom, because they get to use some empty d orbitals. So let's practice. We have xenon and difluoride, so I have 8 plus 14, 22. So we're going to do the same thing. So notice, 2, 4, 6, 8, 10, 12, 14, 16. Sorry, that's just a single bond. 16, 18, 20. Oh no, everybody has an octet, but I still need more electrons, so I'm just going to put them on my central atom. And xenon is in the 3rd row, and below, it's like quite below actually, it's in the 5th row. So that can handle it. Cool. So xenon tetrafluoride. So, we have 8 plus 7 times 4, so 36 valence electrons. So xenon, we'll have those fluorines. Put them around. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Oh no, we need to get to 36. So I'm going to do 34, 36. Okay, the last one. I'm actually going to draw this one and talk a little bit about our formal charge. So phosphate. Phosphate has 5 valence electrons from phosphorus, 24 from oxygen, and 3 extra. So I have 32 valence. Now, I wish I could erase that. Let's see. Awesome. So we're going to just draw our phosphorus with our 4 oxygens. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. You might say, hey, 32, I'm good. But you're not good. You're fine. But now we're going to do formal charge. So each of those oxygens are exactly the same. So we have 6 valence, minus 6, minus 1 bond, so -1. Each of those have a -1 on it. Now phosphorus has 5 valence. It has 0 non-bonding electrons and 4 bonds, so it has a formal charge of +1. So this is what I was talking about a few slides ago about moving electrons. So it doesn't matter which one I move, but phosphorus is in the 3rd row, so it can have an expanded octet. So what it can actually do is one of the lone pairs from the oxygen can be removed, and we can make that a bond. What this will do is make my formal charge for phosphorus and oxygen that I adjusted 0 and 0, making this have a less formal charge overall. So that's where this phosphate can have it use the expanded octet from phosphorus by having 10 electrons around it. So I'm going to write these structures. You can practice them, and then I will pause so you can practice, and then you can look at the answers. Okay, here you go. Here are these last ones. Some of them fulfill octets, some of them don't around the central atom. Aluminum actually is going to act pretty similar to boron, but again, this is usually considered a nionic compound, so if that one tripped you up, then I won't. Just don't get too hung up on it.